Welcome to the 8th lecture of the online course that is non-traditional abrasive machining of materials. So, today after having discussed at length about the horn design etc., we will take up certain aspects of some other aspects of the machine as regards the feed, the acoustic head design and some other aspects. We will also try to recapitulate and tie up the loose threads from previous days discussions. So, let us start right away. This shows one of the typical head designs, feed mechanisms that we might be employing. Up till now, we have come across one of the feed mechanisms in which a dead weight was being used on one of the pans of a weighing balance, and on the other side it was pressing the workpiece against the tool. I will just draw that figure for a quick recapitulation. It was very simple. It was something like there is a pan, there is yet another pan. I put a dead weight of my choice here. These two are connected together and they are pivoted here, so that it can undergo this sort of up down motion, weighing balance. And on this side we had the end part of the horn, the workpiece here, and the abrasives were put here. You might say that the abrasives and the slurry, they must be changing the static load that I had in mind when I put this particular W. But when these abrasives are put in, their weight is not very significant, and in order to remove any doubts about the actual static load, there are some holes made here. There are some holes made here through which the particular slurry, the remains of the slurry can remove itself by gravity. This was the one feed mechanism that we had already seen. There are slight variations of this one when we come to the actual machine, and this is one. What is happening here? This is the acoustic head. We are not showing anything inside it at this moment. We are only showing some slides by which rollers through which it can be fed downwards very smoothly, and the horn and the head, this together makes up the machine, and it's having its own weight, and the counterweight is so chosen that it will be leaving a few kgs of weight to make this move downwards and get pressed against the workpiece. So, this is one pulley, this is another pulley, this is the rope, and therefore, this counterweight is just 1 or 2 kgs less than the machine, so that the machine has a tendency to go down under the effect of a weight of 1 or 2 kgs of load, which means 10 to 20 newtons, which is quite high for ultrasonic machining. Here we have another setup. In this setup, we have so the disadvantage in this setup is that every time you go for a different load, you have to put down this counterweight, put another counterweight, etc., and that way you have to choose the particular load. So, this one is USM feeding with a spring force. As you can see here, this is the spring, and the spring is connected in such a way that if it is put under this is a sort of compression spring. If it is put under compression, it will try to apply a force so that it will try to expand. If it tries to expand, what will happen is it will start pushing this particular member downwards. Is that so? Let's quickly check. If it tries to expand, no. If it is fixed, then this will be pulling it up. So, if it is a tension spring, okay, if it is a tension spring, in that what happens is, compression spring is that when compressed it will give you a reaction. Tension spring is when it is pulled, it will give you a reaction. So, if it is pulled, it will try to compress it itself, and if it tries to compress it, if it tries to become smaller in size, it will definitely push this downwards. So, we have a tension spring which is expanded and then put here, and this will press it downwards because it is trying to become smaller. Okay. So, the advantage of this is you can preset the load, okay, by expanding the spring to a particular length, but the disadvantage is that if the length of the spring is changing with passage of time as it's machining and as this is going downwards, the force which it applies will definitely change, even if subtly or slightly, it will change, because the length of the spring will define how much force it is going to apply. Then USM feed mechanisms are also present with pneumatic cylinder, okay, or hydraulic cylinder, just excuse me. Yeah. So, pneumatic cylinder, how does it work? You might be having from a piston, from the power cylinder, you might be having hydraulic fluid or air at a pressure on this side, and this one is connected to the sump, so that the piston will be experiencing a load force which will ultimately push it downwards, and therefore, the whole body will also be pushed downwards. Up till now, you must have noticed something, that is, in ultrasonic machining, we are always trying to apply a constant feed force, and this is contrary to the idea in, say, conventional machining of lathe, milling, etc., where we generally apply a constant feed rate. What do we mean by this? On the lathe, if you apply automatic feed, it will be constant with time. The displacement is proportional to time, but in this case the load or the force is constant. Why so? This is because if I apply a constant feed rate, there is no guarantee that I will be actually removing that material due to the ultrasonic vibration acting on the abrasives. If the rate of material removal is less than the feed rate that I select, that means, if I select feed rate to be constant, and if I select it by some automatic means, it might not be equal to the value of the actual material removed by means of abrasive action. In that case, they will be jamming. The same thing happens in case of EDM. In EDM, what happens is that we use a servo mechanism. We do not select an automatic feed, because if we select an automatic feed which is higher than the rate at which material is lower than the rate at which material is removed, in that case if in EDM we select a feed rate which is higher than the rate at which material is removed, we will have a short circuit, okay, and if it is lower, then the machining will be sluggish, okay, unnecessarily sluggish. So, here we understand that in these different cases we are trying to have a particular feed force, but it is not always so. You can also select a particular feed rate by use of a particular load. Let us have a look how it can be done. Here we have a bleed cylinder. What is a bleed cylinder? Here there is a very small orifice through which liquid can pass from one side to the other. Now, why should it pass from one side to the other? This is because this particular head which is existing here, it is connected rigidly to this piston, and therefore, the weight of the head will try to bring the piston downwards. Now, ordinarily the piston would have gone down in a flash under gravity, but it cannot, because this hydraulic fluid here is going to resist its motion downwards. So, what happens is the rate at which this liquid can pass through this very narrow orifice, that decides at what rate this will be fed downwards. Okay. So, this sort of mechanism is also very popular, because the hole or this aperture which is present here, it can be adjusted. So, if it can be adjusted, we can have higher feed or we can have lower feed, depending upon the diameter of this aperture. So, this is called feed with bleed cylinder. So, the load is being applied by the head, and the the aperture controls the amount of fluid which can pass through. So, these two things interact to produce a particular feed rate. If possible, I will set you a numerical problem on this also. Now, we come to another interesting case, that is the design of the acoustic head. And in this case, of all the possible designs like piezoelectric effect, magnetostrictive effect, we are dealing with a magnetostrictive acoustic head. What do we mean by this in the first case? First of all, whenever we are talking of vibration, okay, being given to the tool, we have to first of all produce vibration. How do we produce vibration? This is done by by some property of materials. I can mention two properties like piezostriction and magnetostriction. What do they mean? There are some materials which, when magnetized and demagnetized, will change their dimensions, okay, in a direction perpendicular to the direction of direction in which they are, say, electrically charged, say piezoelectric crystals. Okay. If you apply a voltage on these two phases, you will find that the dimension changes in the other direction. Same thing with magnetostriction. So, in magnetostriction, what are we going to do? We are going to apply some coils around this magnetostrictive material, and then we are going to apply a alternating magnetic field. If we apply an alternate magnetic field, this will go on changing its dimension. Excuse me. So, first of all, it will become smaller, larger, smaller, larger. So, if this happens, a particular vibration will be set up, and tuning can be done so that we have a frequency matching with its resonant frequency. Now, what do we have in this particular figure? We are showing that there is a, first of all, there is a encompassing body, and inside it we are having this magnetostrictive material. So, this is that magnetostrictive material, but however, we have written stampings of magnetostrictive material. Now, what does that mean? Stamping, it means that we are going to have a stack of, let me draw it here to make it clear. Just one moment. So, we are going to have a number of such separate layers of magnetostrictive material. What kind of magnetostrictive material? Say nickel or some alloy of nickel, some alloy of iron and aluminium, some alloy of iron and nickel, something like that. Different magnetostrictive materials can be used, permalloy, permadur, etc., etc. What do we do with that? Now, if we have such materials all together in a block, and we put coils all around it, we will be setting up, if it is alternating this magnetic field, we will be setting up eddy currents inside. Eddy currents will be going. Why? Because of self induction. This will, if there is a coil, if there is another coil, if there are magnetic lines of force passing through and interacting with this coil, this will also start having, there will be the rise of induced EMF here. Same thing, this will act as a coil as a whole, and there will be rise of induced EMF, which will drive a current here, unnecessary wastage of energy, and ultimately we will have lot of material, a lot of energy wastage. So, what is the solution? Break them or separate them into separate laminar pieces of magnetostrictive material with insulation in between, so that they stop such eddy currents from circulating. That is good. So, we make stampings of magnetostrictive material. Stampings of magnetostrictive materials, they are used here, and that brings the total wastage. That means, the heat produced from wasteful circulation of current, that is reduced, but you cannot reduce it fully. That is why there is a jacket of cooling water all around, and water comes in, water goes out, and the head is kept cool. As we know from experience, head always has to be at a low temperature in order to act properly. This is the generator which is sending that AC alternating signal, and therefore, we generate this way this particular vibration. So, magnetostriction and piezostriction. What are typical piezoelectric crystals? You can have PZT, lead zirconate titanate, and so many varieties are there. I will be giving you some notes also, supplementary notes, which will have these details, which you can study yourself. We need not use up our useful time of interaction going through all these details. So, I can promise you some notes in this regard. Now, we come to a very interesting aspect of ultrasonic machining, which is the effect of different input factors on response or output characteristics. So, let us see, if you look at this one, for example, static force changing on this side and MRR plotted on the other side. What is static force? The force which is pressing the workpiece and the tool to each other with the grids in between. So, the theoretical curve is like this. Now, let us try to recall what is the relation between MRR and static load. The relation is that MRR is proportional to F to the power 3/4, and this is the typical curve that we expect for that. But in actual practice, we will find that it droops after reaching a particular maximum. That is, with further increase in static force, we do not find an increase in MRR. Why is this so? This is because at higher loads, the abrasive grids are crushed. If they are crushed, they become abrasives of smaller size, and they are not that effective in removing material, because in the same expression the MRR is proportional to the grain size, and hence if the grain size is becoming smaller due to crushing, the MRR comes down. Okay. Now, let us see surface roughness with average grain size. I am changing the grain size, that is very good. So, with that I expect that the material removal rate will increase, and it is increasing no doubt, but I find that tungsten carbide and glass, they are having different rates of removal. Why should this happen? What is the effect of material? For example, how does the material affect it? So, for that, if we remember that tungsten carbide is having higher hardness than glass. So, in the expression for material removal rate, so let us have a quick look. All sorts of terms are there like these, and we find that it has a bearing on MRR, hardness of the workpiece. What about this? This is the ratio of the hardness of the workpiece to the hardness of the tool. So, that also is definitely important, and therefore, this starts affecting. So, if it is h to the power 3/4, if this is lower, so the rate of material removal rate will be higher. But if you notice, this is not dealing with MRR, this is dealing with surface roughness. Now, this becomes important. Why should surface roughness in case of glass be higher compared to surface roughness obtained for material of tungsten carbide? This is because the craters or the hemispherical chunks which are removed, these are small in case of tungsten carbide due to high workpiece hardness. So, it forms smaller craters, this forms larger craters, and therefore, the cumulative effect of having such craters on the surface leads to, that is, gives rise to higher surface roughness for glass and lower surface roughness for tungsten carbide. Okay. So, main reason is smaller craters, larger craters, craters being formed by the hemispherical chunk removal. This is a figure of the tool, showing tool wear. You can see it is not a plain surface anymore. These are some of the parts that we have machined, and this clearly shows the clear surface of glass and the rather translucent or slightly fuzzy or hazy surface of the machined part of the glass machined by ultrasonic machining. These are done by the same tool that you saw just now. Okay. Right. Some more. So, surface roughness, some data. If you have 0.5, if you have 55 microns as the grit size, which corresponds roughly to 280 mesh size, okay, then you will get a roughness RA value of 0.5 microns. If you have 7.8 microns as the grit size, corresponding to 80 mesh size, it will give you roughly 0.2 microns. Okay, RA value 0.2 microns. Now, let us have a quick look at the effects of MRR, effect on MRR by the different input factors. This we have already seen, that is static force rising to a high level and then drooping down. So, we need not visit this once again. Let us take a look at this frequency. Frequency, the theoretical effect is that frequency should be, MRR should be directly proportional to the frequency, okay? Because MRR is, if you look at this expression once again, it is directly proportional to the frequency. So, if frequency is on this side, therefore, the MRR should have come as a straight line, but actually it comes this way. Why? This is because when we are deriving the expression for MRR, in that case we make an assumption, that is 4 times the amplitude is covered in the time period and a proportional amount of time will be required to cover delta t plus delta w. That is an assumption because of which this discrepancy occurs. Okay. I will just repeat, during the derivation we had assumed 4 times amplitude divided by the time period must be proportional to delta t plus delta w divided by delta t. That is actually an incorrect assumption and its reflectance is coming here. This is lambda, that means workpiece hardness to tool hardness. So, if the workpiece hardness to tool hardness increases, that means workpiece is becoming harder and harder. So, tool will be taking up most of the indentation because it is deformable, it is softer and therefore, MRR comes down. Okay. Tool is taking most of the beating and therefore, MRR comes down literally. Achha. Average grain size, if it goes on increasing, MRR is going to go up theoretically, yes, but actually it is found that it starts drooping. Why should it go up? Because once again in this expression we have D here. So, it should be proportional, but instead of that it actually droops. Why? There are a number of reasons for this. One is crushing. When it is becoming more or less equal to the amplitude, it shows a crushing tendency, and also it finds difficulty to enter the gap between the tool and the workpiece, because it is large in size compared to the amplitude. Okay. So, there are some more of such effects to be discussed, but we have roughly reached the time for time limit for this particular lecture. So, we will continue this in the 9th lecture. Thank you very much.